Hello friends, welcome my channels. Today's discussions physics versus mathematician for Ricci tensors. So friends, let's start to discuss for physics that Ricci tensor used for physics. Ricci tensor or curvature used for physics. So friends, Ricci tensors are used a lot of place like general relativity, Einstein fields. Today I want to discuss for Einstein field equations. So friends, you have to learn this is the first equation. First point is R mu v minus half R g mu v plus lambda g mu nu is equal to 8 pi g divided by c to the power 4 t mu nu. So friends, this equations is called Einstein field equations. So I introduced every topic. This is R mu nu equals to Ricci curvature tensor. R is Ricci curvature scalar and G mu nu equals to metric tensor and capital lambda equals to cosmological constant. Capital G equals to gravitational constant. Small c is equal to speed of light and capital T mu nu is equal to stress energy momentum. So friends, we have understood that the equation, this is the Einstein field equation, and we have learned all the terms. What is the meaning of these terms? This is the Ricci curvature tensors. Okay, Ricci curvature tensors mathematical approach I will discuss, but now just initial idea this equations. How can I represent a Einstein field equations? This is the very interesting. This topic is very interesting topic. That's why I discussed this topic. So let's start to know what does mu nu denotes. So friends, mu nu denotes space-time in four dimensions. Zero is time, zero dimension, and 1 is x-axis, 2 is y-axis, 3 is z-axis. So friends, I take a dimension. I am not taking into account the z-axis because it would be difficult to show this t, and would be the time which is shown on the y-axis. y-axis, and xyz are the three spatial dimensions. These are spatial dimensions. So mu and nu basically denotes the space-time in 4 dimensions. Which is used extensively in Einstein field equation. I have been speaking about Einstein field equation. It consists 16 non-linear partial differential equation. 16 non-linear partial differential. So we discuss what is the non-linear partial differential equations. Now we want to discuss number 1, r mu nu. So friends, I have already discussed this is the Ricci tensors. R mu nu is Ricci curvature tensor. So R mu nu is the dimension. How many dimension? 4 dimension. 4 dimension space. Dimension space time. G mu nu is also 4 dimension. Another is G nu, that is also 4 dimension, and T mu, this is also 4 dimension. So friends, whatever you see, that 4 plus 4 8 plus 12 is a 16. So we see 16 equations. We get 16 equations. 6 equations are duplicate, and which makes them a total 10 non-linear partial differential equations. So friends, I have already discussed metric tensor in my videos. You will see that it is represent as a matrix form. So I can write this way: G mu nu can be represented as a matrix. G 0 0, G 0 1, 0 is the time dimension, friends, and 0 1 1 is x axis, and G 0 2 and G 0 3 and G 1 0 and G 1 1, G 1 2 and G 1 3, G 2 0, G 2 1, G 2 2, G 2 3, and G 3 0, G 3 1, G 3 2, G 3 3. This is the way. This is the matrix. This is the metric tensors, friends, and it is represent as a matrix, and this is the symmetric tensor. This tensor is symmetric. So friends, symmetric tensor dimension, I have already discussed that n into n plus 1 divided by 2 equals to dimension of symmetric tensor. So dimension is 4 into 4 plus 1 divided by 2 is equal to 10. So we get 10 components. So our component is component is 10. We get 10 component. So g mu nu can be represented this way. So friends, you see that this is my tensors. I reduced total component is reduced only 10. You see that only 10 components. And now if we see similarly stress tensor T mu nu is equal to T mu nu as it is symmetric. You will see that stress energy T mu nu is called stress energy momentum. So T mu nu is equal to, can be written this way, metric form, T 00 T 01 T 02 T 03 T 11 T 12 T 13 T20 T21. So we see that this is also 16 component and it is reduced into 10 component as it is symmetric matrix. So summarizing Einstein field equations. So friends, you see that this portion and this portion shows the curvature of space time. So friends, summarizing Einstein field equations, you see that this is the summarizations of Einstein field equation. This is the, you can get from every book that it is the equations. R mu nu plus minus half into R g mu nu and plus lambda g mu nu and 8 pi g c to the power 4 t mu nu shows the curvature of space time as determined by the matrix G, and this is the geometric of space time, and it is the matter energy content of space time that equals to matter energy. So we get that geometric of space time is equals to the matter energy matter movement. Sorry, it is not energy, it is matter movement. It is matter movement. Alternative way of writing the equations r mu nu minus half r g mu nu plus lambda g mu nu equals to 8 pi g divided by c to the power 4 t mu nu, and where g mu nu is equal to r mu nu minus half r g mu nu. Here k equals to another factor is I have to write another equations that g mu nu plus lambda g mu nu equals to k t mu nu. So friends, I just use this equation equals to these equations first. These equations first. How? Because g mu nu this portion is the g mu nu, and this portion is k is equal to 8 pi g. Here I mentioned that 8 pi g c to the power 4. So this is the another alternative way I can write this way. So friends, 8 pi g c to the power 4. Here this k value, k is called Einstein gravitational constant. Einstein gravitational constant. Einstein gravitational constant, and c is equal to speed of light. Speed of light. Speed of light in 4 dimension. And g is Newton gravitational force, and small g equals to Newton gravitational force. So friends, this is the, and pi factor is actually coming when we are computing the surface area of a sphere. So we will see into that it actually comes from Poisson equation of gravity. Poisson equation of gravity. Poisson equation of gravity. How the gravitational force is taken into account. 8 pi factors comes from Poisson equations and computation on its spherical surface. Now Einstein tensors. Einstein tensors. Einstein's tensor is defined G mu nu equals to R mu nu minus half G mu nu. This is called Einstein tensors. Einstein tensor is symmetric, means G mu equals to G mu nu. So it represents the space-time curvature tensors. This curvature is due to matter distribution through the space-time fabric. In fact, the so-called gravity force is nothing but this is curvature which let matter move. Curvature gravity force equals to curvature. Gravity force equals to curvature which let matter. So friends, we have just learned physicist view. Let's start to learn mathematician view about Ricci tensor. So Ricci tensor for mathematicians. So in case of mathematics, we need to learn covariant differentiation. Covariant differentiation. So A I J dot K and A B dot C comma M. So we need to learn covariant differentiations. So let's start to discuss. And it can be written this way, equals to del AI J comma K and A B dot C divided by del X M plus A B C P J K into gamma I M plus A I P K A B C gamma P I gamma I P M. And plus dot dot up to a plus a I j dot dot p a b dot dot c gamma k pm, and this is also gamma j pm, and minus a I j k p b c gamma I gamma am am amp. This is the dummy index and a is replaced in here. This is the second kind Christoffel tensor. Minus a I j k a p c to gamma p b m minus dot 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 minus a I j k a b up to p can retain gamma p p c m. This is the covariant. This is the covariant mixed tensor. I just show that mixed covariant and contravariant differentiations, friends. We need to learn covariant and contravariant differentiations. This is the mixed differentiations. Mixed differentiation. So friends, how can I write ai j m equals to del ai divided by del xm plus a p gamma I pm, and when the contravariant differentiation, this is the contravariant differentiation, so this then it should be plus, and ap and gamma p is the positions. When the case is double gamma a I j comma m, then this is rank, the tensor rank is 2. Then it can be written del ij divided by del xm plus a p j. So my tensor is gamma I pm, gamma I pm plus a I p gamma j m, gamma j pm. This is the contravariant differentiations, and now I discuss covariant covariant differentiations. A I comma m equals to del A I divided by del x m plus minus AP gamma p I m. Gamma p I m. Similarly, if I will say, I will write I j m, then del A I j divided by del x m minus AP j gamma p I m minus a p I p is equal to gamma p j m. This is the way of the covariant differentiation friends. So friends, I just show mixed differentiations, and I am just showing covariant differentiations. So very easy. And now we will learn Ricci theorem and Ricci tensors. And now we have to learn d del g del x k is equal to gamma j k comma I plus gamma I k comma j. Number 1 and number 2, del g I j del x k equals to minus g I h gamma j h k minus g j k into gamma I h k. So friends, these theory are very important for Ricci theorem. Now I discuss Ricci theorems. So friends, Ricci's theorem is fundamental metric tensor Gij or Gij and del ij are covariant constant such that del r Gij equals to 0, del r Gij equals to 0, del r del ij equals to 0. So friends, this is the covariant constant. So covariant constant means it is the 0. So del r Gij equals to, we know the covariant derivative del x k Gij minus gmj gamma. When the covariant, then we see minus. When the contravariant, we will see plus. Minus g im gamma m jk and del Gij now friends, I discuss this formula. This is my formula del g xk. This formula I have to use in here. So this is the del g ij. These are not del g ij. This formula I will use in here. can be written this way, that ijk comma k plus jk comma I minus j I comma k minus I comma j comma k. So friends, whatever we see ijk, this portion and this portion and this portion is cut, and this portion and this portion is cut, so it is 0. Similarly, del r gij is del xk gij plus gmj gamma imk plus gim gamma j mk. And friends, we know this formula is, I have already discussed this formula, del gij divided by this formula I have to use, and gamma ghk equals to, can be written okay, I will use this formula in here. And it is equals to minus gmj gamma imk minus gim gamma j mk plus gmj gamma imk plus gim gamma mk. So friends, you will see that this portion and this portion is cut, and this portion and this portion is cut, after that 0. So friends, you see that all the portion is 0. Similarly, we can see that del r del I j is also 0. Now we discuss that this is the Ricci theorem and Ricci tensor in the mathematical view. Ricci tensor. The Ricci tensor denoted Rij. The Ricci tensor denoted by Rij is a. So friends, let's start to discuss Ricci tensors in mathematical view. The Ricci tensors denoted by Rij is a covariant. So friends, must remember it is the covariant tensor. It is covariant tensor of order 2 and obtained by the contracting the indices m and k in the Riemann-Christoffel tensors is Rm Ijm, and you will see this is the contracting, this is the covariant and covariant index and contravariant index are same, so we get a contraction. So we whatever Rij is equal to Rm Ijm, and mixed Ricci tensor is Rij is Gim into Rmj, and Rij is equal to ln root over G I comma j gamma ln root j comma n. So friends, we have learned Ricci theorem and Ricci tensor, and also it is in case of mathematical view, and you will see that this is my Ricci tensor, rank tensor. It is rank is 2, and it is the covariant tensor. This tensor is covariant tensor. So friends, we see that physics view and also mathematics view in the Ricci tensors. Ricci tensors we apply in Einstein field equations, and also it can be used in general relativity. A lot of case we use Ricci tensors. So friends, thanks for watching.